So thank you very much for the invitation. I'm very pleased to talk to you about a beautiful problem, which is the Schrödinger problem, and and Alfred already talked a little bit about this. Maybe you won't see completely the link between the last slides of Alfred and what I'm going to talk about. Unfortunately, I will not write a lot of mathematical formula, and the Bernstein-Schrödinger system will not be on my slides, but the connection is that you've seen many exponentials in Alfred's talk, and the exponential is in convex duality with the logarithm, essentially y log y, where you have convex duality. And this y log y, this logarithm, is inside the relative entropy here. So, and this will be the connection. I will call this the primal problem, and the exponential pops out with the dual problem, and there is, this is the link. Okay, so what I'm going to talk first is about optimal transport. And I'd like to introduce the notion of a very well understood now notion of interpolation on the set of probability measure. So X, to fix the ideas, it's usually a state space. But in this talk, we'll think of a Riemannian manifold. P of X is the set of all probability measures on the manifold. We'll fix two marginal measures, mu0 and mu1. So the idea is to interpolate between mu0 at time t equals 0 and mu1 at time t equals 1. And they are on the state space. So you can think of many means, many ways of interpolating. Of course, the easiest one is the affine interpolation, where you take the barycenter of mu0 and mu1. And it gives you something like this. If you want to transport this mass profile at time 0 onto this final mass profile at time 1, and you perform this affine interpolation, what it gives you is this thing. You see? And you do not respect geometry here. You didn't see anything here. And your space, you do not visit the space in the right form. So what we have done with this affine interpolation is that we have operated an infinite speed transportation, okay? And we don't want this, because we destroy the geometry. What we want transportation, not teleportation, okay? So what we are going to talk about is really this kind of things. You see, it's much better, because you have some geometry here. And so to perform this, what you should do, this is the initial mass profile, the final one. First of all, you have to decide of a transportation plan. So you want to choose a target for X. X will arrive at Y. So you choose a transportation plan, and I call it T. This is a mapping. Y equals T of X. T is for transportation. Then you use the geometry. Once you have the couple XY, the blue line is a geodesic. Suppose there is only one between X and Y. Okay? So now you have this family of geodesics. And now you just follow the geodesics. This is mass at time 0. And at time t, as you can see, we are on the geodesic between X and Y. And all the mass flows through the geodesics. And this is what is called a displacement interpolation. All right. So now we would like to find a way of building interpolations that are respectful of the curvature. The best thing that we could hope, and indeed it will happen, is that observing many interpolations could give you some information about the curvature. And what happens is that you can have some information about the lower bound of a Ricci curvature. Okay? So, as you know, several geodesics will give you information on the curvature. For instance, if you have only two geodesics on a surface, then the fact that the Gaussian curvature is positive here has the effect that the geodesics have a tendency to get closer to each other. Okay? On the contrary, if the curvature is negative, they will go apart from each other. So now, okay, we have taken a little bit of the geometry, all the geodesics, but now we want to build this interpolation. How should we do? This is how should we choose this transport map? Clearly, we do not want any shock, because if you perform some shock, for instance, if you couple this one and this one, then you will mix, and there will be overlaps, and you will not see very clearly how the curvature acts. And if you do, this is what is said here, but in fact, what can be done, the best way to do it is to perform optimal transport. And so doing, so I write the original Monge problem, which is the problem of finding the best mapping T, such that T, the push forward of mu0 by T is mu1, and you minimize some cost function. And in the situation of Riemannian geodesic, what you can do is to minimize the square of the Riemannian distance. Okay?
But times 0 of dx also transformed because x is transformed.
Sorry?
Mu0, the reference measure is transformed.
No, you have mu0 at time 0, and you see this is y here. Y is equal to t of x, and this is hidden in this formula because mu1 is the push forward, the image measure of mu0 by t.
But in the back measure dx doesn't transform.
Sorry?
In the back measure dx is not transformed.
Oh, it's not Lebesgue measure. This is mu0 of dx. This is the measure. You only transport mu0, okay? This could be on, well, there is on a manifold, but there is no Lebesgue measure. This is the notation, d mu0. Okay, so what happens there? In case you have a positive curvature, then this is mu0, this is mu1. What happens? You know that the geodesics have a tendency to get closer to each other. So it will give you this picture, because as you can see at the end of the travel, of the journey, geodesics get closer to each other. So if you had targeted at the origin something like this, then you would have get something which would have been much smaller here. So you have to spread up at the beginning, because they get closer to each other, and then they shrink at the end. So this is a typical picture of what happens in a positive curvature world. If you have a negative curvature, then geodesics have a tendency to spread out, and you will get this. At intermediate time, there will be shrinking, okay? All right. Now, how to measure this tendency to get fatter or to get or to shrink? It's possible to have a very precise quantitative measurement of this phenomenon, and it has been discovered by several authors. Well, the last one were Max von Renesse and Theo Sturm in 2004, and what they have shown is that if you consider the relative entropy H of mu t with respect to the volume measure, then as a function of time along any displacement interpolation built on the quadratic, on the square of the Riemannian distance, then you have some convexity property. For instance, if k is equal to 0, the curvature, the Ricci curvature is positive, then what you get is that you observe a convex function. Okay. The term W2 is connected to the quadratic optimal transport, but I won't get into detail there. And I have no... Sorry. Ça fonctionne plus, je n'ai plus accès à... Il faut peut-être le relancer là, non? Fermé là, non?
J'arrive pas à avoir la souris.
Tu veux changer de laptop?
Éventuellement, si jamais ça... Ça a l'air de repartir, ouais. C'est bon. Ah. Merci. So, this very beautiful result has been the starting point of a theory, which is called the Lodge-Stone-Villani theory. And the idea is that instead of considering a Riemannian manifold, you can consider any metric space. So you have a distance, you can consider the square of this distance, and you can talk about mu0 and mu1, and you have an entropy, which is only a measure theoretical object. So you have all the ingredients to work with a generic metric space. And in fact, if your metric space is a geodesic space, then this could be, this is indeed a candidate to be the definition of a lower bound for the Ricci curvature on this space. So this is a different notion. I see Jan is here. This is a different notion of the rough curvature of Jan, but they are very much connected in some sense. Here, just for the specialists, we'll look at W2, a quadratic optimal transport, while Jan Olivier's curvature deal with the W1 optimal transport. Okay, now, how much time do I have? Oh, it's great. Okay, now I would like to talk about entropy and something which is going to be related. What we are going to build right now is a regularization of this interpolation. I will call them entropic interpolation, and they have been designed by Erwin Schrödinger in 1931. And these are precisely the connected with the regularization that Alfred talked about at the end of his talk. So the physical picture is the following one. Now you consider a huge family of particles, and you think they are arranged at an initial profile which is close to mu0. But these particles live in a heat bath so that they will perform a Brownian motion. There will be some positive temperature. Okay? Now, the law of large number tells you that the final profile at time t equals 1 should be very close to the prediction of the heat equation. So you have to follow the heat flow starting at mu0, and it will give you some profile. And the law of large number tells you that you will observe with a very high probability your system very close to, let's say, I would call it mu1 here. And the question of Schrödinger is the following one. Suppose you do not observe your system close to mu0, mu1 at time 1, but close to some profile, mu1, which is far away from the expected profile. Well, this will happen with an essentially zero probability. Exponential minus c is positive, you see, and a huge number. So it's essentially zero, but still it's positive. So now you can condition on this very rare event, this is a large deviation problem, okay? And conditionally on the fact that you observe this very rare event, what is the most likely, the most probable event? So you will build an interpolation between mu0 and mu1, which will maximize the conditional probability, which, or in statistical physics term, which will minimize some free energy, okay? Or maximize some entropy for the physicist and minimize the relative entropy of the mathematician, because we have a convex function here. Okay, so we are on a compact Riemannian manifold. I will call capital omega the set of all paths, the trajectories. Capital P and capital R are path measures, probability measures on the path space. And R is for reference measure, and we choose for simplicity the Wiener measure because we have Brownian particles. Now the Schrödinger problem is this problem. We want to maximize this conditional probability, but doing large deviation theory, Sanoff's theorem tells us that you have to minimize the relative entropy of P with respect to the Wiener measure, R, subject to the constraints that the initial and final marginal are prescribed to be mu0 and mu1. Okay? And if you want to do this, then you have to solve the Bernstein-Schrödinger system of equations that Alfred talked about. Okay? And this gives you some answer, which is the answer of the Schrödinger's question, and we call it the entropic interpolation with respect to R. Okay, so to summarize, at zero temperature, when the paths are very regular, you have geodesics, what we have done, we have built displacement interpolation by solving an optimal transport problem. Now, there is a positive temperature. The particles live in a heat bath, and what we obtain, we build entropic interpolation, and we solve a minimal entropy problem, this one. Recall at negative temperature, at negative curvature with zero temperature, you could observe something like this. Now, at positive temperature, there is some fuzziness, okay? So you smoothen the heat equation, there is some convolution, and what you obtain is something like this. So I cannot show the computation, but if you compute the second derivative of the relative entropy with respect to the volume measure, you will get essentially exactly the same thing as you would obtain at zero temperature. There is some gamma-2 calculus, and to perform this computation, you have to consider the two directions of time, backward and forward direction. Without doing this, you're lost. If you do this, you have pretty simple computation to perform. Okay, now we want to show that this is a regularization of the displacement interpolation. So we want to decrease the temperature, and the way to do it is to slow down the particles of the heat bath. Therefore, instead of considering the Wiener measure R, we consider a sequence of Wiener measure, R K, where you see K will tend to infinity, so you have this slowdown sequence. This temperature is 1 over K, essentially. So this is K equal 1, so you see this This is supposed to be the drawing of a Bronner bridge between X and Y. Okay? And if K is equal to 10, you will get something which is 1/3 of this, essentially. And at the limit, you will recover a geodesic, the geodesic between X and Y. Now, K is equal to 1, so you have some temperature, and you look at the behavior of the large number of particles, capital N. So what you do is large deviation theory, you deal with Sanoff's theorem, and when minimizing, what you obtain here is a cooperative behavior for all the particles, and what you do is simply the Gibbs conditioning principle. Now, if you look at only one particle and let K tend to infinity, then you will get this convergence of the bridges to the geodesic. This is an individual behavior, and we will have to deal not with the Sanoff theorem, but with the large deviation principle of the slowing down. For instance, with this Wiener with 1/k, this would be simply Schilder's theorem in large deviation. And what we do is to mix both the effect, and what we obtain is a mixture, a superposition of these two behaviors. So there is maybe one message in my talk is that this slowing down sequence encodes some geometry. You will see you will get these bridges converge to the Dirac measure at the geodesic. So is it? It's okay. So now I will talk briefly about the results. So we have already seen that displacement interpolation field curvature. This was essentially the result by von Renesse and Sturm. The same thing happens with entropic interpolations. They also fill the curvature in exactly the same way. It's possible to prove that this entropic interpolation, as the temperature goes down to 0, converge to displacement interpolation. And also, of course, because there is the heat equation somewhere, the Laplacian, there are regularization of this displacement interpolation. This is really interesting because, I didn't say it before, but this displacement interpolation built on the optimal transport are not regular. There is a very bad behavior. The trouble with regularity are huge. You see, you have to deal with the Monge-Ampère equation, and which is, well, a not so easy equation, and there are a lot of work, essentially by Caffarelli and his co-workers, about the problem. So you have to deal with this. Now, with the entropic interpolation, you will replace Hamilton-Jacobi equation by Hamilton-Jacobi-Bellman equation, which is much easier to work with. And, well, the tool, technical tool, is all these results can be expressed properly in terms of gamma convergence. Also, oh yes, what we did, we used the Wiener measure on a manifold, okay. But you can play exactly the same game with, for instance, a random walk on a graph. And hopefully you could have beautiful results about this lower bounded curvature. But you get into a trouble, absolute trouble of computation. So if you want to look at discrete curvatures, read the papers by Yann Olivier, because the rough notion allows easy and very efficient computation, while this notion could be, in some sense, more precise, but at this time, it's not effective, because nothing cancels in your formula, and you have to do gamma 2 calculus with 16 terms instead of 4, and well, I couldn't do it. So you can play the same game with Finsler manifold. The idea would be this: you have a smooth manifold, usual differential manifold, with a Finsler structure. So how to simulate such a Finsler structure? The idea is you can play a jump process. So it's a time-continuous jump process, but the slowing down is simply that you will require that the jump process will jump in a very small ball of radius 1/k, for instance. And then you require that this particle should be very far away, should be at y after time 1. But essentially, you will, since you slow down, your particle will have to do so many rare events that it will have to compute to optimize something and to find a geodesic. Okay, this is kind of perverse game. You see, you have a particle here. You asked this particle to be here, but essentially this particle doesn't want to move. But you condition on the fact that there are maybe 1 billion events that has to be performed to get into the final position, while this particle would have done maybe 1 or 2 events. Okay? So, conditionally on the fact that it has to do this, it will choose the shortest path. This is the way to force geometry and to get the geodesics. And this was the second message of my talk. You can also play, I thought of it a couple of days ago, with interpolations with varying mass. Instead of having, for instance, a random walk or a diffusion or something, now you can play with branching particles. So you remove the constraint of having a constant mass. The number of particles is varies randomly, and at the end, if you ask, well, I would like to have twice as mass at time equal 1 that time equals 0, then you will see that your particle system will branch much more than it dies, okay? And it will probably give, I don't know, this is work in progress, as it's written here. Finally, well, it's still possible to use this Schrodinger problem to think of dynamical theory of diffusion processes, for instance, because this problem is exactly the analog of the Hamilton least action principle in classical mechanics, and you can play the same thing with random walks. The connection with the curvature is that, of course, the Euler-Lagrange equation that you will encounter, which will be a stochastic one, the stochastic Newton equation, of the same kind of the stochastic Navier-Stokes equation that Mark talked about at the end of his talk this morning, then you have to deal with acceleration, the stochastic acceleration, and clearly acceleration is related to curvature. So, oh, it's okay. With our last slide, I want, of course, there is this very beautiful paper by Schrödinger. I say very beautiful, but it's written in German, and I couldn't read it properly. So there is another one in 1932, written in French. You can get it on Nundam. So it's very easy to get. It's published in the Annales de l'Institut Henri Poincaré in a wonderful French. And it talks with the end of this problem. Of course, there is absolutely no large deviation, no probability, because probability were formalized 2 or 3 years after by Kolmogorov, Bernstein and Kolmogorov. This was at the same period. And the connection with the entropy is that he does combinatorics. So there are a lot of factorial, and he writes this thing with equal Well, this is, so now it's true if you, and this is the connection with the entropy. Okay, if you have some time, you can read the book by Cédric Villani, the big yellow book, 1,000 pages, about wonderful book about optimal transport. I want to quote also my friend Jean-Claude Zambrini, who has been working on this subject for a long, long time. And the recent papers about the random walks on the graph. This is a paper by myself and a postdoc student, Giovanni Conforti, about the Wiener measure and the convergence as the temperature goes down to 0. The first one to notice this properly is Toshio Mikami in 2004, but you won't see any entropy in Mikami's paper, but optimal, stochastic optimal control. And well, the other papers are by myself about also the random walks and the diffusion. And that's it.